Today, we're going to be watching tap stripping. Yep, that genuinely is worth doing. And I plan on hopefully relating it to possibly one of the most remarkable equations accessible at school maths level. So let's watch a tap drip. I promise it's probably not going to be as dull as you're expecting. Here goes. Drip, 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 drip. Okay, so that one probably was as dull as you were expecting. But then all of a sudden, let's add just a little bit more water. Drip, drippity drip, 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 drip. Ooh, something that was predictable just took on a bit of a weird pattern. It's still in a pattern, but it's a slightly more odd pattern. The drips were no longer equally spaced, and you had this kind of single drip, and then you had the kind of dribbly drip happening. Not impressed yet? There's one more. Drip, drip, drippity drip, 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 drippity drip, 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 drippity drip, 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 drippity drip, 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 drippity drip, 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 drip. Whoa! Now that one, we'd lost all pattern completely. And that's really odd. Something that should be predictable has suddenly become incredibly unpredictable. Now, for centuries, physicists sought to perfectly understand the world around them. But really, the harder they looked at some of the things that they were meant to be looking at, the more perplexing they became. Simple systems, things like dripping taps, or populations of animals, or snowflake formation, or weather, all really could escape their grasp, even though the simplest models that they could create, the simplest systems that they could study, seemed to lead to these peculiar outcomes. The more data they collected, the more disordered the observations became, and the less mathematical they seemed. That was until the beautiful equation we're going to look at today was revealed, and both the sheer simplicity and yet the mind-boggling chaos of these systems actually could be understood. Now, we're going to look at a couple of different models, and we're going to start with a simple population model. So let's look at a simple population model to start with. The very most basic model would be to say that a population grows at some rate r, and let's take r to be 2. So this would mean for our population, we're starting with 2 rabbits. If you don't understand why we need 2 rabbits to start with, go and ask biology. But those 2 rabbits in a year become, very quickly, 4 rabbits. And 4 rabbits become 8 rabbits. And 8 rabbits become 16 rabbits. And 16 rabbits become 32 rabbits. And 32 rabbits become 64 rabbits. And everything keeps going until eventually the whole world is just rabbits. That model would look like this as a recurrence relation. So our next year's population is just r times this year's population. And at the moment, we're taking r to be 2. That clearly is not a very realistic model. It needs a little bit of work because the whole world is not covered in rabbits. And this isn't how populations really work. Well, except maybe humans who, you know, one of the few that throw off the limits and have a spiraling population and use up all the world's resources, and slowly the world dies and blows up, and that's it. But uncontrolled population growth like this isn't what usually happens. Instead, most species of animals have a limit. Either they're short of food, or they've got predators that will eat them, or maybe there's just overcrowding. But all of these aspects limit how big a population can be. So a much more realistic model, and this turns out to be incredibly good at predicting real populations, is the equation at the bottom here. That next year's population is going to be the reproduction rate times this year's population. That bit's still in. We still have that aspect. But we've got this other term now, 1 minus Pn, which is limiting our population. Now I should point out that Pn here is actually the percentage of some theoretical maximum population. So as we approach that theoretical maximum, that starts to limit our population growth and stops our population getting very big. So this term here becomes really important because that builds in these factors like food scarcity or predators. There'll be more predators if there's more prey. Or as space runs out, our population can't grow so fast. So all of these things stop our population growing to 100% of its capacity. And how it grows depends exactly on whether the reproduction rate pushes it up really fast or whether this limit on population growth pushes it down. Simple enough, right? Well, kind of. Let's follow a couple of examples through. So here, to start with, we have a population, and the population has a reproduction rate of 0.98, and we've started it off at 50% of total capacity. Well, we can see what's happening here. Our population's in serious decline. Our reproduction rate is so low that our population is declining until we go extinct. Now actually this isn't so unrealistic for the real world. There are things we can do. For example, the pandas in China, we've actually taken away some of their food source and their reproduction rate's gone down. It's dropped below 1 and they've gone extinct for that reason. Not even because of any other factors that are involved. We've literally pushed the reproduction rate so that they've gone extinct. However, most populations don't do this. So let's have a look at another population. Here I've picked a population with a growth rate, or a reproduction rate I should say, of 2.1. Well, that's interesting. It grew initially, we started small and it grew initially, but it's leveled off at 52-ish% of its total capacity. That's its stable point and it's got stuck. Now actually it doesn't matter where we start. So we could look at the same population and start at 90% of capacity. Well, then overcrowding and population factors mean that our population drops drastically initially. And then bumps back up and levels out at exactly the same equilibrium. So these are like the limits that we found in our lessons in the last 2 weeks. These are the limits of the recurrence relation and where it's going to even out. So we would expect our population to be 52-53% of the potential maximum population that's possible. Okay, so these ones are fairly predictable and they do what we might expect, I guess. But maybe let's start with something a bit different. Sometimes systems are not going to end up in a stable and predictable format. The physicists and the biologists, they smile when you get the image that you've got on screen just now because it's predictable. It does something that we would expect. But if we raise our reproduction rate to 3.1, all of a sudden we get this bizarre behavior, a system which is oscillating. Still predictable, but not very pretty. And actually this is something that is seen quite often, particularly in things like mice and ants and bees, populations which oscillate up and down in a sort of repeating pattern between two values. However, not necessarily completely stable. Okay, let's push this one step further. Let's look at the reproduction rate being 3.7. So here we're starting and up, down, up, down, up, down, up, down. And it seems to be oscillating, but not in any kind of vaguely predictable way. And in fact, it's really messy. It oscillates between 7 or 8 different values across a given time span. And it settles into this really chaotic cycle. So, one more graph for you. We're going to put these results together and look at what that overall image looks like for different reproduction rates. So here's a diagram. Now this graph along the bottom axis shows us our reproduction rate. And up the side axis here, it shows us the limit that model goes towards. So we already saw that if we pick 2.1 as our reproduction rate, we ended up with, and this point's pretty much on the graph here, we ended up with 52% being our limit. We were leveled out at about 52% in the maximum possible population. Now let's start looking at what goes on. So as we pull along, well, actually, if our reproduction rate is really, really low, and in fact, if it's less than 1 is our key figure, our eventual limit is that extinction that we already saw. So along all of these values, if our reproduction rate is less than 1, our population will go extinct. That makes sense. Now let's ramp it up above 1. Well, here we go. So as we see, if our reproduction rate gets higher, we would expect our population, the limit of that population, to become higher and higher and higher. And that kind of makes sense. The more there's reproduction, the more it fights against those other factors such as prey and lack of space, etc. Now we're increasing here, but it's leveling off. So actually we can see that our maximum population, if we account for all those other factors, seems to level off at just over 0.6. So leveling off. And remember, we're looking at our limit here. And this point at 3 is absolutely critical, because this is showing us no longer is our population nice and stable. Our population will oscillate between these two values shown on this graph. So we're oscillating between two values here. That's at 3.1. Then suddenly at 3.4-ish there, about 3.4, we start oscillating between 4 values. So these are getting less predictable, these populations, because we're now oscillating between 4 values. Up at 3.6 here, it starts to oscillate between 8, then 16, then 32, then 64 values, then 128, and by this point it's oscillating between so many values that our population has actually become chaotic. So at this point it just oscillates really, really, really randomly. And we can see that as we extend forward, that becomes even more the case. As we go along here, it becomes ever more chaotic. Now it's worth mentioning, and this is not something I want you to follow too much at the moment, there is actually a little island of stability at about just beyond 3.8, where actually we go down to oscillating only between 3 values again, randomly, and then just bigger than that, it becomes chaotic again. Now, how does this fit with real systems? Well, with real systems, sometimes physicists see that they're really stable. So things like the weather, some patterns are really stable and really predictable. Sometimes there's a bit of uncertainty and it varies unpredictably. Sometimes those systems become incredibly chaotic and prediction becomes almost impossible. So if you wonder why the weather forecast is so often wrong, it's because we're dealing with a system which does this. It's so unpredictable, it's chaotic in its behavior, and so when we reach a pattern that's chaotic, making a reliable forecast of the future weather is almost impossible. So let's go back to taps for a second. What did we see with our tap? We saw a regular pattern. It was drip, 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 drip. Well, that's this stable system where there's one nice curve. We saw a system with our tap where it went drip, drippity drip, drip, drippity drip. And that's like this. That's these two possibilities coming out with our tap. And then we saw a chaotic system here. How does that relate to populations? Well, fairly straightforwardly, in fact. Instead of a reproduction rate involved in our population, we have a flow rate. That flow rate, if it's low, will give us a very predictable pattern. As the flow rate increases, something unpredictable starts to happen. So if you're watching a dripping tap, or the weather outside and wondering why the forecast's wrong, the answer is not because physicists don't understand it, but because nature is sometimes, even from the simplest of equations, a lot more complex and chaotic than you could ever expect.